Okay, so oh, not I didn't update this. Today's plan is 6.5 and 7.1, average value of a function and integration by parts. The quote of the day today is from my favorite grad school professor at University of Pittsburgh. He's now retired, Professor Bill Layton. I took several classes from him. Really interesting guy, had a lot of great quotes and great ideas, taught me a lot about math. But one of my favorite quotes of his is, good decisions come with experience, and experience comes from making bad decisions. So kind of unfortunately, the only way to get to proficiency is through a little bit of, discomfort and pain. And that could be, actually just making a bad decision and learning from it, or that could just be, something didn't quite go your way. And I think when that happens, when we either make a bad decision or when something doesn't quite go our way, we tend to take one of two forks in the road. We tend to either, kind of write that experience off and just ignore it, or either try to forget about it, or maybe not so much for people in Calc 2, but a lot of folks in math will have a bad experience with math or have a tough time with a course, maybe fail a course, and then they're just like, I'm horrible at math. I want to avoid math at all costs. Maybe not so applicable to this class in that example, because I think most of you are probably pretty good at math, but in the lower level courses, this is certainly an issue. And they try to kind of avoid it, where maybe leaning into that discomfort a little bit and saying, okay, what did I do? What decisions did I make? What could I do better next time? And then have another go at it, right? To kind of get up, dust yourself off, have a little bit of grit, a little bit of conscientiousness, and say, okay, what can I change to make the next time go better? And that could be, maybe you don't do so great on homework. Maybe you're really struggling with a topic, or maybe you didn't do so great on an exam in Calc 1 or something, and reviewing that process and saying, okay, what could I do to improve on this next time to make myself more likely to be more successful? So I think that's definitely the better approach to take, although that can be quite a difficult thing to do. Okay. So moving on to average value of a function. So the average value of a function can be denoted a few different ways. Sometimes it's just something like f subscript AVE for f average, particularly if the independent variable is time. In physics, so a lot of times you'll see it denoted as angle brackets with the f in the middle. So this is like the time average of the function. Or if the independent variables, usually if it's not time, you might see it as f bar. So kind of reminiscent of something like x bar from statistics, where kind of a bar over a variable sometimes means average, although putting a bar over something can mean a lot of different things in a lot of different contexts across math. So that's certainly not, a ubiquitous meaning for that notation. But what is the idea of an average? If I had, say, 10 numbers, let's say x1 through x10, I might think of something like x bar, or kind of the average of these numbers, as being the sum, whoops, over the number of those numbers that I added together. So I add up the 10 numbers, I divide by 10, and that's my average. I could kind of maybe think of this in a picture a little bit as, this is forcing the issue a little bit here, but I could think of a graphical depiction as being like data point 1, data point 2, out through data point 10. And I'll make a bunch of boxes, each of which is width 1, and which is height, say x1, x2, x3, has height of, oh, I don't want to put bars over those, but has height of each of these data values. And this might have height, x10, which would mean the areas of each of these boxes is x1, x2, x3 through x10. And then I could see that the numerator here is kind of like, well, it's adding up all of the xi's, x1, x2, x3, and so on. But that's really just adding up the areas of those boxes. So the numerator is the area, the total area of all these boxes. And the denominator is the interval width. It's the number of boxes we added up, but because each box is width 1, the number of boxes we add up when we stack them next to one another consecutively like this, that just turns out to be the interval width. Right, so it's the sum of these numbers divided by going from 0 to 10 is an interval width of 10 units. And it doesn't so much matter whether I start at 0 and go to 10, or whether I start at 100 and go to 110, or negative 50 and go to negative 40, as long as I have kind of a contiguous chunk of interval I'm working with. So this basic idea of average that I think we're all used to from, I don't know, like grade school or something like that, where you add up the numbers and divide by how many you added up. We can, it's a little bit forcing the issue, but we can rephrase it in terms of a graphical concept. And really, we can even go a step further now. We can look at these boxes as really a piecewise function. So this is f of x on 0 to 10, a piecewise constant function in this case. Let me go over to the side here, I guess. So if I say the area, the total area, I could even rephrase that as the integral f of x dx. And as long as my function is piecewise constant, where the pieces are each 1 unit wide and all contiguous and all of those things that I said before, I've rephrased my simple kind of like grade school version of average in terms of calculus. What is my interval? Well, let's just call this a to b at this point. So we'll do integral a to b f of x dx, and then divided by what's my interval width then? B minus a. Now, this might seem like a goofy thing to do. Why would I force the issue with such a simple thing to rephrase it in terms of calculus? Well, the reason is that if I think of f as a piecewise constant function with all of these caveats I said before, that's just another way of saying what's the average of these 10 numbers. But if I want to construct something that's an average of a function where I remove some of those caveats, maybe it's not piecewise constant, maybe it's not, you know, just these boxes of unit width or whatever. Maybe I allow f to be just an integrable function on a to b. I can generalize this idea to a much broader class of functions than I could, you know, something like over here. So if we kind of take the very basic idea of average, rewrite it in terms of in a way that is more generalizable, where I can remove some of those caveats and I don't just lose all semblance of meaning or interpretation. So I don't have to have piecewise constant function of unit width pieces anymore. I can just have an integrable f, an f that I can take the integral of on a to b. And this is my definition of f average. Right, it is the area under f from a to b divided by the width of the interval over which I calculated that area. It's just the direct generalization of our, you know, simple, good old average of so many numbers that we know, that we've known for a long time. Okay. Something switch out of red. Red's a little bit harsh. Let's go to green, make it look like Christmas. Something that's an important idea related to the average value of a function is the mean value theorem for integrals. So we know the mean value theorem, let's say for derivatives, or just the mean value theorem. I'll come over here and just remind us of that. For f, differentiable on a to b, continuous on closed a to b, we have that that this is true for some c in a to b. So this is our general mean value theorem, or our first mean value theorem, or mean value theorem for derivatives. But we have a corresponding mean value theorem for integrals. And it looks fairly similar. Let me actually rewrite this a little differently. So we could also state this way. Right. At some point, the derivative is the same as the slope of the secant line from the left to the right endpoints. But we also have an integral version of this, that f of c equals 1 over b minus a, n over a to b f of x dx, for some c in the interval a to b. Or in other words, for some c, f of c is equal to the average value of the function. Okay, so let me push this down a little further, and let's think of a picture here. Let's think about what f average kind of does, and then think about why this ought to be true. So let me say I have from a to b, and I'm just going to use a positive f, but all of this works for negative f's or positive and negative f's, as long as we respect the interpretation of area as signed area. But it's just a little easier to visualize with positive functions. So here I have my function f on a to b. I have some area under f. Now, the way that I like to think of f average, if I imagine that this is like a volume of sand, maybe I have like one of those little like anthill containers, or what do they call it, ant farms or something, where there's just like, a centimeter deep or something of sand that's kind of in this, going along this curve. If I go and I kind of jostle this back and forth until all those grains of sand kind of, let's pretend that the sand's not compressible, so it doesn't kind of crunch down anymore, but it just evens out. Well, the sand is going to even out by taking some of the sand that's kind of up here at the top of this peak, and that's going to fall down into the valley. And because gravity keeps pulling down, that's not going to want to come back up. Things are going to generally want to go from hills to valleys and kind of settle out that way. So eventually this is going to become a flat volume. And that height is f average. That's really what f average is. The kind of arithmetic mean, the average of these, say, 10 numbers, what that says is that if I replaced each of these with x bar, if that was my data set, just 10 copies of the exact same number x bar, the sum of these 10 would be the same as the sum of these 10 copies of x bar, right? 10x bar equals this sum. That's really what we're saying. If I replace my kind of variable data with just, if I replaced each of those data points with the same number x bar, then that sum would be the same. So for things where it's important to kind of conserve the overall total, the sum, that's maybe a reasonable statistical technique to use. And that's kind of what we have here. We are saying that if at each location, instead of the variable f that's sometimes a bit lower, sometimes a bit higher, if I replaced it with a constant height, then the appropriate height to use will be f average to maintain the same amount of area below. I should have made my blue f a little more extreme so it's a little easier to see what's going on, but you can see that there's kind of a hill there and there's a couple valleys that are going to be filled in. So this green area includes like some of this area up here in the hill, does not include this area in the valley. The red area includes the valley here and this little piece over here, but does not include the hill. The red area and the green area are equal areas. So if I replace my, variable f that sometimes is higher, sometimes lower with the constant y equals f average, the area under f average between A and B is the same as the area under f between A and B. And that's what we're saying here. And at this point, I think I've kind of used all of my colors, so I guess I'll go to black. It's kind of more clear what we're saying here from the mean value theorem, maybe intuitively why it ought to be true and graphically what we're saying. Really what we're saying is that there's going to be at least one intersection here. Or in other words, kind of what I'm saying is I can't have a situation where I have like a hill like this for f, and then somehow like f average is all below that hill. Like what happened to this sand that's above f average but below f? It doesn't have anywhere that it could have gone. Or vice versa. I can't have an f average that's wholly above f. Again, for the same reason that I'm claiming that these two areas under these curves are the same. Well, where did I get all of this extra sand to build up to that level? My f average needs to be kind of in between f minimum and f maximum. And one of our assumptions, very important assumption, is that f is continuous on A to B. So we have really kind of an intermediate value property going on here. We've got to have at least one intersection. In this case, it looks like there are two intersections, previous case, three intersections, but we have at least one. Remember with the mean value theorem and intermediate value theorem, those are statements that there exists at least one of these such C's. There might be one or two or five or 10, but there's at least one. Hopefully that clarifies a little bit, with these pictures, kind of what the average is, what it's doing, and what this mean value theorem says. When I copied this over, my picture didn't copy. Give me 1 second here to just fix that. Let me try to copy this again, and if I can't get it copied, then I will just draw it again, but I don't want to take all of the time to draw it if I don't have to. Copying can sometimes be a little bit iffy on OneNote. All right. Gonna work for me this time. Okay. Good, it came over this time. Don't know if it came over and didn't save or if it didn't come over initially and I just missed it going through. But we got it working now. Okay, so given the graph below, which now is actually below, that's always helpful. Approximate the average on 0 to 12 and approximate d of 12. So v average, this is a graph of velocities, and we want to approximate d of 12, the distance traveled in these 12 seconds. So I have 4 points. At time 0, I was going 0 kilometers per hour, traveling with 0 velocity. At time 4, I was at 40. Time 8 at 60. Zoom in on this a little bit just in case you're on a small screen. You can see a little better. At time 8, I was at 60 kilometers an hour. Time 12 at 70 kilometers an hour. So these are my kind of anchor points. And I want to compute kind of an average velocity over this time period, 0 to 12. And I noticed that I don't have an algebraic expression for v, but I have some data. So I have a little bit of flexibility in how I choose to go about this problem. I need to approximate integral 0 to 12 of what? Of v of t dt. This is just 1/12, but this is what I need to figure out. I could, I suppose, use maybe a left Riemann sum or a right Riemann sum, but I think in Calc 1, when we looked at those, we kind of saw that for an increasing function like this, the left Riemann sum is always going to underestimate the area, and the right Riemann sum is always going to overestimate the area. And it's, you know, for only a few boxes like this, for only a few subintervals, they're not going to do a really great job. I might be able to take another approach. Maybe there are some more complex methods that I could use, and we'll actually see some more of those later on in chapter 7. But something that I could imagine doing is something like this, using 3 trapezoids instead of 3 boxes. So instead of, say, a right Riemann sum, which would overestimate by all of this, by using this trapezoid, I underestimate, but it seems like by much less. And vice versa, if I had, well, if I used, I might have said that backwards. If I used the left Riemann sum, my box height would be 0, and I'd underestimate by all of this. If I used a right Riemann sum, I would overestimate by all of this. And I think visually it is pretty clear that the trapezoid is going to get me more accuracy than either of those methods. So I can just connect these 2 points with a straight line instead of with this curve. Look at, well, in this case, it's a triangle, but look at the triangle or trapezoid and find its area, do that 3 times. And that's going to give me an estimate for the value of this integral. So let's do that. So I have, let's see, I can use green. I have area 1, area 2, and area 3. So my triangle in area 1, my base is 4 units times my height. This point here is 4, 40. So this is height 40. And then we have 1/2 base times height, or 2 times 40 is 80. Area 2, and let's check our units here. We might as well keep track of our units. 1/2 is just a unitless quantity, is just from 1/2 base times height. My base, time in seconds, and times my height is kilometers an hour. So this is a unit of distance. And we probably will want to fix that unit of distance a little bit. It's like kilometers times seconds per hour. So let's come back in a minute and look at that unit conversion, but we'll save that for a little bit later. But we do at least get something that is kind of a distance. When we integrate velocity, we should get distance, and that's basically what this is. Area 2, I have a trapezoid. What is the formula for a trapezoid? Well, it's the base times the average of the heights. So base width of 4 again, times the average of the heights. 60 plus 40 over 2 is 50. So 200 units. And then area 3, again, a trapezoid, the area is the base width times the average of the heights. Again, a base width of 4, 60 to 70 is the average is 65. So what's that? 240 plus 20, 260. I can add these together to get an estimate for the integral. That's approximately what? 460, 540. And unfortunately, again, that's in units of kilometers, seconds per hour. So, so I know that I have what? How many seconds are in an hour? Well, there's 60 seconds in a minute, 60 minutes in an hour. So I need 3,600 seconds. My seconds divide out, and I have that my integral is approximately 540 over 3,600. We could probably do a little bit of simplification here. 54 over 12 times 360. What else could we do? We can definitely divide out a 2. 26 over, let's do 12 times 180. And then 27. And then we have some factors of 3. We have one factor of 3 in the 12. We have, and that leaves me with the 4. We have a factor of 9 in the 180, which leaves me with 20. So I have 1/80th of a kilometer is my integral. Oh, I have to be careful. This is seconds. 1/80th of a kilometer per second as my average. And my integral is 12 times that. So I have V average is 1/80th kilometer per second. And then my integral, this is approximate. My integral is approximately 12/80ths kilometers. So what's the approximate distance I traveled in these 12 seconds? Approximately 12/80ths of a kilometer, because I was going at average speed of 1/80th of a kilometer per second. As a mathematician, units make me cringe, but but in a lot of these physics problems, I do try to address the whole units issue. Are there any questions on this? Does everybody see mainly why we need to find an integral and why I chose to use this kind of trapezoidal method to find the integral instead of, or to approximate the integral instead of, say, a left or a right Riemann sum? Those are the main math questions here. And then messing with the units was more of like a physics or science kind of thing. Okay. So we'll go through this example in the supplement, looking at the average velocity of blood in a blood vessel and going through the problem with this formula. With this formula. I mean, it is the same formula, but And then maybe asking ourselves, do we think that that's the most appropriate formula to use in this kind of a sense? So we'll see that in the supplement. That's a little bit of a more nuanced question to ask is, okay, we have a function. We can just crank out, say, V average, the average velocity of blood in the blood vessel, by just computing some integral of this function and just plugging it into our definition. But is that a sensible thing to do? And kind of the short answer is, well, there's a nuance that we're not really taking into account if we just do that. So probably not a completely sensible thing to do. We want to do something maybe a little bit differently. Any questions on average value of a function? This is a smaller, a smaller section, not a really big section. Okay, so chapter 6 was on some applications of integration, finding volumes, dealing with work and average value of a function. So chapter 5 from Calc 1 was a little more theoretical, right? Building up to the fundamental theorem of calculus and substitution technique. We went a little more applied. In chapter 7, we're going back a little more theoretical, a little bit more abstract, and we're going to be learning some new integration techniques. So we have a few integration techniques already. What do we kind of have already from, say, Calc 1? Well, we have the simple kind of understanding that an integral is an area. There are some integrals of some functions that we can just interpret them as areas directly, maybe a part of a circle or maybe a triangle or a trapezoid, and I can just find the area geometrically. I don't need to use calculus at all. That's obviously not super common, but that's a possibility. Of course, we have the fundamental theorem of calculus. This is really the foundational technique. It says that if I know a function for which the integrand is its derivative, then I can do the integral pretty easily. And we have the substitution rule that kind of inverts the chain rule. And now we're going to build off of this. And the first technique that we're going to go through, and often in Calc 1, I kind of introduced this idea, so you might even be a little bit familiar with this already. But the first technique we're going to go through is integration by parts. So substitution is kind of related to the chain rule from derivatives. Obviously, fundamental theorem of calculus kind of relates integrals and derivatives, right? So when we have these new techniques, a lot of times there's going to be a relationship between the integration technique and some derivative technique or rule. Integration by parts is related to the derivative rule, the product rule. So let's write out the product rule. The derivative of f times g is f g prime plus gf prime, or plus f prime g if you wanted to write it that way. So now what if I integrate everything? If I integrate left and right sides, I get fg equals the integral of fg prime dx plus integral of gf prime dx. And it's pretty typical in integration by parts to relabel these function names, f and g, which we usually use f and g for the functions in the product rule. In integration by parts, we typically just call u f of x, and we relabel g of x as v. So just relabeling, f of x, g of x turns into uv, f turns into u, and then g prime of x dx, note that that's just the differential of v. This is dv. Is g prime of x dx. So I can wrap that whole g prime of x dx under a dv. And I don't know why my integral signs are different sizes. Like I said, sometimes when I copy in one note, and if I'm not super careful about proofreading, then sometimes crazy stuff happens in the copying. So these integral signs, they're not different sizes for any good reason, just some goofy syntax thing with one note. And then the second integral, g, is v. And then this whole f prime of x dx, that is du. So that's where all the pieces came down, right? This here, all that I did was relabel f and g to u and v, and then to collapse the g prime of x dx and the f prime of x dx into a differential dv or du. And now I can solve for this guy in terms of the others. Integral of u dv is uv minus integral of v du, because this has to go to the other side. And this is my integration by parts formula. Integral u dv equals uv minus integral v du. So the difficulty in doing integration by parts is, number one, deciding whether this is an appropriate technique to use. Maybe this technique doesn't really get me very far in this problem, similar to how, there are some problems that substitution isn't really going to help you at all. And if I decide that integration by parts is a good technique to use, or if I just want to use it and kind of see where it leads me, then deciding what to make u and what to make dv. So really, in a kind of rough sense, what does integration by parts do? If I rewrite this, integral of u dv is uv minus integral of v du. What it does is it moves the derivative from one of my functions to the other. So integration by parts moves a derivative in a manner of speaking. In other words, to go from the left side to the right side, g prime needs to become g. So this g prime needs to be integrated. So when I pick something to be dv that's going to become v, I probably want to pick something that I can integrate. If I pick a dv that's like e to the x squared and that's it, I'm not going to get very far, right? I don't know how to anti-differentiate that. And then likewise, I need to pick something for f that when I differentiate it, I mean, at the very least, it doesn't get terrible, but usually I'm trying to leverage this. Usually this is the part that I want to leverage, that there are a lot of different types of functions that when I differentiate them, they actually get simpler. So I really want to make sure that my f doesn't get worse when I differentiate it, but a lot of types of functions get simpler when I differentiate them. X differentiates to 1. That's a much easier function to work with than x, or log x differentiates to 1 over x. Maybe that's a bit simpler in some contexts, right? So this is really what I'm trying to leverage, is that I can differentiate f as long as I'm able to integrate what I choose for dv, as long as I'm able to integrate this second function. What I choose for f is usually the thing that I'm trying to make simpler when I hit it with a derivative. So that's the kind of, 1,000-foot overview, the strategic overview. And then the kind of tactical side of things, the technique is using this formula. So I want to pick something for u that when I differentiate it, it gets simpler, and such that what's left over for dv is reasonable to integrate. So I want u prime, simpler, and dv to v possible. If I want to put all of that into just kind of, a couple lines here. And then, of course, I also need to be careful with my bookkeeping, right? Integral of u dv. I need to make sure that between u and dv that I've used everything that's in the integrand and nothing that's not. All right, so let's look at this example. Integral of x e to the negative 2x dx. Now, a side note, I mean, we're in the integration by parts section. When you're doing the homework, you're going to be in section 7.1, and that's a pretty darn big clue that you need to use integration by parts. But it is always good to just ask, is there something simpler to do? And maybe I should even squeeze in here algebraic simplification, right? Sometimes there's some algebra that I can do to simplify things and just make the problem easier. You know, is this representative of some simple area I can compute? No, it's not. Is there any algebraic simplification I can do? No. Do I immediately recognize this as the derivative of a function? I mean, maybe if that was e to the x squared, I might, I might be able to recognize that kind of quickly, but I don't really recognize this as the derivative of a function. Is a substitution going to work? I mean, I could try to substitute like negative 2x, but I don't think that's going to get me anywhere. The du is going to be negative 2. So what am I going to do with that x out in front? So I don't think any of my simpler techniques work. Let's look at integration by parts. I need to try to find a factor that when I differentiate it, it gets simpler, and what's left over is not too bad to integrate. U equals x is a pretty good choice for something that gets simpler when I differentiate it. It differentiates just 1. Then what does that leave me for dv? E to the minus 2x dx. Is dv something that I can deal with? Is it something that I can integrate? Yeah, I don't have any problem integrating this basic exponential function. Have I used everything in my integral and nothing that's not in my integral? I have. So I've split this integrand into u and dv. U I can differentiate, gets simpler. dv I can integrate, and it's not too bad. Du equals just dx. V, if I want to integrate this, I have something that looks like e to the negative 2x. I don't need the general antiderivative. I don't need the plus c. If I differentiate this, I get negative 2 e to the negative 2x. So I need to correct that constant out in front. If this step is something that you're not comfortable doing in this kind of guess and check method, or just kind of the recognizing as a derivative method, you can go and do a substitution here for this step as well. If you wanted to, write out a few more of the details, but the kind of guess and check method often works pretty well for substitution problems. Now I have integral u dv. That's going to be uv minus integral v du. So there's v, and then du is just dx. Can I do this integral, right? I need to be able to do this integral, and I would like to end up with an integral that I can either do right away, or at the very least, I've taken a step forward, right? At the very least, I have made some progress. And yeah, I can actually do this integral now. Let me simplify a little bit. Super important to be careful with all the bookkeeping here, just keeping track of all the negatives and things and all of that. So this negative a half comes out and makes a plus 1/2. And then I can do this last integral. E to the negative 2x integrates to something like e to the negative 2x. Again, if I differentiate this, I get a factor of negative 2 in front. To get rid of that, I need a negative 1/2. That's my integral. And then at this point, remember I asked for an indefinite integral. I ought to respond with the most general antiderivative, most general function that whose derivative is this integrand. So I put a plus c on at the end. I didn't worry about putting the plus c on here because that's just going to complicate things. I just need an antiderivative up here, but I want the most general one down here. And rewriting. And if you wanted to, I suppose you could factor out that exponential. I'll just leave it like this. Now, something to note here, something that's kind of interesting. If I thought of a substitution problem, integral sine of 2x dx, and I did u equals 2x, du equals 2 dx. Let's even make this integral of 2 sine of 2x just to make it even easier. Then I have integral of what? Sine of u du is negative cos u plus c. I don't want to report this as my final answer because the original question was in x, but I substituted in a new variable u. I really want to go one step further and report my answer in terms of x, right? So when I'm doing a substitution method, I use this u that I assign to be something from the integrand, and I do some work, and then I kind of like, there's like an x world and a u world, and I have to switch back and forth between them. Or if this was a definite integral, I would have to change my bounds of integration because the x's turn into u's, so then I got to rephrase the bounds of integration in terms of u. But note that integration by parts, I mean, it's a little confusing because we're using u and v. So we see that same u from what we usually use for substitution. But we're not actually substituting anything here, are we? This was just scratch work. The real mathematical, this thing equals this thing equals this thing, always stayed in x. This scratch work, this u and v stuff, this is just for me to kind of take some notes and be able to correlate the integrand that I'm working with. The integrand that I'm working with, be able to correlate that to the corresponding pieces in the integration by parts formula. I'm just kind of assigning some things to be u and some things to be v or dv so that I can match up the pieces from the formula, but I was always in the x world. So there's no actual substitution going on here. I don't need to substitute back in to get back in the x world. I don't need, if I had bounds of integration, I wouldn't need to change them anywhere. So super important little detail. Substitution rule, we go from the x world to the u world, and then we got to come back to the x world. Or if we have a definite integral, when we go from the x world to the u world, we have to rephrase the bounds of integration in terms of what they ought to be in the u world. Not the case here. So I just want to point that out because I think that's a point that can be a little confusing between the two, especially because I didn't make the choice of the variables that folks tend to use, but we tend to use u for substitution and u and v for integration by parts. Are there any questions so far? Okay, so another example, we might be able to get through one, maybe two more examples. The integral natural log of 3x dx. Now I look at this, let me just copy my formula down and cross my fingers that this copy works okay. Okay, that went well. Sometimes OneNote amazes me at how well it copies things, and then sometimes it seems to be a little glitchy, and maybe I'm the one that's glitchy, I don't know. So I have an integral here, integral log of 3x dx. And again, if I go through my process looking at previous integration techniques, I don't really think any of those are going to work very well. So I'm up to integration by parts for my next technique. And we're covering this in the integration by parts section. So maybe that's a hint that integration by parts ought to work here. But I look at this and I think, well, I have a little bit of a problem. Like, I'm looking for a product in my integrand. Here I had x times an exponential. I don't really have a product here. Well, wait, or do I? I really kind of do, right? If I wanted to force the issue, I could say this is times 1 dx if I really wanted to. But I do have a factor, this log, that gets simpler when I differentiate it. I would like to pick that to be u so that I get to differentiate it to make it simpler. What does that force dv to be? Well, dv just has to be dx. Right, that's all that's left over. Can I do this integral? Well, yeah, that's not bad. Integral dx is just x. Right. So the difficulty of this problem is really just realizing that dv can just be dx. du, what is this? Well, differentiating log of 3x is 1 over 3x, but times the derivative of the inside is a 3, so this is just 1 over x. This might seem a bit strange at first glance, but remember your log properties. Log of 3x is log 3 plus log x. Log 3 is a constant, it differentiates off. Derivative of log x is 1 over x. So if we think about it a little further, it all, I think, makes sense. So I have u dv. I have used everything that's in my integral and nothing that's not in my integral. I've done all the bookkeeping okay. I've got myself set up to move to the right-hand side of the formula, uv minus the integral v du. And du should have a dx at the end. X over x is 1, integral of dx is x. And I'll put my plus c on here for good measure. And if I wanted to, I could factor out an x. Any questions on integration by parts so far? So another note on this is just like kind of all of these, recognizing, getting your brain used to kind of recognizing things as derivatives. Whenever you were used to recognizing how to take a derivative, now we are thinking inverse with the fundamental theorem of calculus. Getting used to figuring out what you ought to make u in the substitution method. These are things that at first are kind of confusing, but you go through 5 problems and it gets a little better. You go through 15 problems and it starts to almost become second nature, right? But especially with these integration techniques, the more experience you get, the more slightly different types of problems you see, the more you maybe go down a wrong road. Maybe you pick the wrong thing for you and you get a step in and you say, oh geez, that really didn't work. Rewind a little bit, try something else, and that does work. The more that you do that, the more practice you get with it, the easier it becomes to see what you ought to pick for u or du, or what you ought to pick for u in substitution, or even zooming out, the easier it becomes to see what integration technique is likely to work for this problem versus maybe not likely to work. And even when you get really used to it, like when you look at people who are much better at calculus than me, some of these like folks at like the MIT integration bee and stuff like that, they have math folks have integration bees instead of spelling bees, where they put hard integrals on the board and people try to like race to work out the solution. Even folks that are really good at calculus, that they can sometimes look at a problem and struggle a little bit and have to maybe try this technique and say, oh, that didn't work. But maybe in trying that, I learned something. Maybe I went down that path. I kind of failed and made a bad decision in a sense. I failed, but maybe I learned something from that about the problem. And that informs my next decision. My next decision can be better because of that, instead of me just getting annoyed, ripping the paper out, throwing it away, and then, not learning anything from that. So sometimes if I, tried a substitution method here, if I tried u equals 3x, does that get me somewhere? Maybe it doesn't, but maybe I gain some information from that failed attempt that I can bring back to the problem and, make a second attempt that's even better. Okay, I don't think I can do this problem justice in 2 minutes. So I think we will stop there.